Okay, so the question says the table shows part of the instruction set of a processor. The processor one general purpose register, the accumulator, and an index register. Um, this is, I believe, a very standard question that we usually get for our um, assembly language. So yeah, what we've got to do is we've got to complete this trace table now, guys. Of course, trace table questions are usually very important, and in my opinion, they're like pretty straightforward. So all you've got to remember in these trace table questions as well, and also the trace table questions that you get, for example, for a program. That you've got to fill up the trace table of a certain program and so on and so forth, which is a part of basically your practical papers, paper 2, paper 4. What you got to do is just make sure that you smartly trace it out. Okay. Now I hope you know this, but very quickly the point is, now see, you've been given this table. This table is actually telling you that what does each of the assembly language instruction mean, which means let's say, for example, let me just talk about very quickly. Let's say this particular instruction. This one, add. What does it say? It essentially means that if you've got add and you have an address, then what's going to happen? You're going to add the contents of the given address to the accumulator. So whatever is in the accumulator, you're going to add the contents of this particular given address to the accumulator. So on and so forth. It's actually, there is everything explained over here. So that's the first thing. The second thing is that you're given, your main memory is starting at a certain point, and you're given a certain set of execution of instructions which is actually happening. So you've just got to trace it out. Now a lot of people pointlessly struggle in this question. Well, this is maybe one of the most straightforward questions. All you got to do is make sure that you read the instructions and you follow it all. That is it. All right, let's have a look at it. um so it says complete the trace table for the program directly in main memory when the following characters are input. So the first input that we'll be getting is an A. Okay, but let's see what does it say. So when we started off, it says IN. Okay, now let's go back and have a look at what does IN mean. IN mean that key in a character and store its ASCII value in the accumulator. So what's going to happen, guys? What's going to happen is that you're taking an input from the user. So the user actually inputs what? User inputs A. So it says whatever the user inputs, you're going to store the ASCII value. So the ASCII value for A is 65. So we're going to fill up the accumulator with the value of 65, right? And what's going to happen is that we have this in the accumulator, the value of 65. And the second thing is obviously that, what we have is if you go through the columns, we have the instruction address column, we have the memory addresses column. So what we've got to make sure is that in the instruction address and the memory address, we also fill up those as well. What's the value going to be in the accumulator, and along with that, we're also going to have a look at what the instruction address or the memory address is going to be. So for this particular case, we started off with instruction address 70. So that's what it is. Obviously, the instruction is going to go on one by one. So it says, I'll move on nextly to instruction number 71. So let me just fill it up. This is going to be 71. It says CMP 100. So let's see what the CMP does. It is a compare instruction. It says compare the contents of accumulator with the contents of address. And yeah, so what we'll do is we will compare the contents of the accumulator with the contents of the address. So CMP 100, what is at 100? There is a 68 at 100. So we'll just perform the compare. Okay, now the compare happens usually when compare is used. After compare, there is usually a jump instruction based on what you should do. So compare is more or less like the if statements that we have. So the next instruction 72, we just compared it. Doesn't seem like to be any changes in any of the columns. So we move on to 72. What does 72 say? 72 says JPE80. So what does JPE say? JP means following a compare instruction, jump to address if compare was true. So following the compare instruction, jump to address if the compare was true. So basically, JPE 80 means that I'll move to address number 80 if the compare was true. So my value is 65. I compared it with the 100. The value in 100 is 68. So the compare is not true. So I won't do anything. I'll move on to the next thing. What we'll do is we'll compare with 101. Now again the same process. When you compare one, it says jump to 76. So let's say at 101 I have a 65, right? And in my accumulator there was another 65, so the compare will be true. So I'll jump to 76. So basically what's going to happen is that this jump to 80 instruction, for now it will be skipped. So what we'll do is we'll actually move on to number 76. So after this we're going to have a um just a sec. Yeah, after this we're going to have a, yes, of course it is going to 74, then it's going to be a 76. We jump from that because again the accumulator had 65 and the address, the sorry, the value at 101 is 65, so then the compare is true. So we will carry out this jump instruction, which is JPE 76. So move on to 76. Now 76 says LDD102. So what does LD do? Let's go back, have a look at it. LDD says direct addressing, load the contents of the location at the given address to the accumulator. So whatever the address we have, we'll go to that address, we'll load the particular value in that address to the accumulator. So let's see, it says LDD 102. So what do we have at 102? We have a 100 at 102. So 100 will be loaded into the accumulator. Yeah, so what we'll do is that we will load the contents in, uh, yeah, sorry. So what we'll do is we'll LDD 102. So the contents of 102 will be loaded into the accumulator. So this is going to be 100. Um, Now going back and running the next thing, what does it say? It says 77. It says inc accumulator. Inc is for increment. It says add 1 to the contents of the register, which register you're referring to. So the register that's being referred to over here is accumulator. So basically in line 77, after instruction address 77, what we'll have is we'll have this incremented by 1, so it becomes 101. Line 78 says STO 102. STO is for store. So let's go back, still read it out. STO address says store contents of the accumulator at the given address. So what we'll do is we'll go on and store the contents of the accumulator at the given address. Okay, so the contents whichever are the accumulator, will store it in the given address. So it gives address number 102. So when I run 78, I'm going to go to address 102, which is here, and I'm going to store the value which is in the accumulator, and the value in the accumulator is 101. So my memory address 102 is, by the way, updated. It was initially 101, like the value in that. Now the value in this is going to be 101. Let's go on to the next thing. It says 79 says jump back to 70. So when I go to 79, this is a jump instruction. Let's see what is jump to. Jump essentially just goes on and goes back to the address. Just jump to the given address. Now when it says jump to the given address, we'll jump to 70. When we jump to 70, very simply what's going to happen is that, I mean, from 79 we're going to go on and jump back to 70, because remember it asked us to jump to 70. And now once we jump to 70, the whole process is going to repeat, right? Because it starts off with an in, which is basically taking an input. This time around the input is what, guys? The input is going to be a D. Okay, and I mean, I hope you remember, but I'm still going to go through this again. And the point is that because it's jumping on to the next thing, so what we have is we're going to have D is 68. So the value 68, the ASCII value will be stored. Then moves on to, sorry, it won't be written here. It will go to the next line, because when we went to 79, when we went to 79 we had a jump, right? So we went back to 70. So basically this is going to be a 70, and the ASCII code for D, which is 68, is going to be in this line. So we've got to be careful about these little things. All right, now of course we'll go back to 71. 71 is again a compare. 72, I mean, I'm going to go through this because we just went through all this, so I hope you understand this. Compare with 100. 71 is compare with 100. When I compare with 100, what is in 100? Um, the memory location 100 is a 68. So because this is a 68, It says JPE80. Now we compared it with it, and now when we want to 72, now let's see what was going to happen this time. So when we compare it with the memory address 100, now the input we got was 68, right? Because it's a D, the ASCII value in the accumulator. Now at the address 100, we have a 68. So the compare is true, right? So since the compare is true, what we'll do is, because remember again, JP says that if following compare jump to address if the compare was true. Since the compare is true, we'll move on to address number 80. So now what we'll do is we'll move on to address number 80. Because there's a jump instruction, we're going to jump to it from 72 onwards. We'll jump to 80. Now what does 80 do? Let's see. 80 says LDD 102. So let's go back and look at what is LDD. So LDD means load the contents of the location at the given address to the accumulator. So what do we have at 102? At 102, we had 100, but remember, we changed the, in following this instruction, we actually updated the value. So when I'm going to do LDD 102, it is actually going to store, it's going to load up 101 in the accumulator, not 100. And the reason for this being the fact that we just updated it, right? So in the previous run of the instruction. Okay, now going back to this, it says decrease the accumulator. It's actually pretty straightforward. The increment is increasing by 1, this is subtracting by 1. So in 81, we're going to do one, it's going to become 100. Let's see what does instruction number 82 says. Instruction number 82 says STO 102. So we're going to store this in 102. So what we'll do is we're going to store this in 102. So 102 is going to again have a value of 100. Then we'll move on to 83, which is jump to 70. We move on to 83, which is going to jump to 70. And the next thing, when we move on to stem 70, we'll stop here. Why? Because when I go back, I move on to 70, it's going to ask for an input again. But the question tells us that you only have to do till the second input, so do not trace it any further when the third input is required. So this is pretty straightforwardly, what we had to do for this 4 mark thing. And it, I think, becomes pretty quick to be done once we actually have our we know what each of the instructions mean. It doesn't take this much of time, but I hope it's clear. All right, let's move on to the next question. um, okay, very quickly, guys. Very quickly. We've got and an or an XOR, and or XOR are again are but just bitwise operations. So when I say bitwise operations, that essentially means that it's going to perform bitwise operations on bitwise each of the bit. Bitwise means again it's going to do each of the bits. So let's see, it says the context of memory address 300 represent unsigned binary integer. Write the denary value of the unsigned integer memory address 300. Well, we've just got to compare it in denary. So remember what we're going to have: 1, 2, 4, 8, 16, 32, 64, 128. Now when I add all of them up, it's going to become what? 2 plus 4 plus 32 plus 64. So that's going to become 96, 102. Simple as that. Okay. An assembly language program needs us if bit number 2 memory address 300 is a 1, complete the assembly to perform this test. So you've got to test if the bit number 2 in 300 is a 1. So basically this means that I've got to test whether, so basically what I've got to test whether is that this is a 1. Okay, the bit number 2 is a 1, right? So it tells complete the assembly instruction to perform this test. Well, this will be an AND 4. Now, how this is going to happen now, guys, remember, whenever you have to test a 1, or if you test a 1, what you'll do is you can AND that particular bit with a 1. Okay, because see, if that bit is a 1, you'll get a 1. If that bit is a 0, you'll get a 0, right? It would not matter that what it will not matter that what you've taken. For example, like when I do and 4, so 4 in your denary is what, sorry, in binary is 8421, so it's going to be 001. 0. So I'll do 0, 1, 0, 0. So since I'll get a 1 over